launched on your final project. So if we okay, so if we look at the syllabus and dial down to today. So here we are on the 7th of March, which is amazing. And so, so everybody listen up. So the final project proposal is due on the syllabus, and currently it's due tonight at midnight. I'm going to move that till tomorrow. I'll give you a little bit of time. So tomorrow at midnight, you need to turn that in. Go ahead and just put something down. Remember, you're totally allowed to change your proposal. You just can't add members to your team. That's all. So make sure you've got your team set, and you can kick members off, but you can't add members. So anyway, and then if you get kicked off a team, well, then you have to submit your own proposal, and you can submit it late. That's okay. I won't penalize you for that. All right. If you scroll down, you'll see that on the 11th of April, so it's a little more than a month away. That's when we have the mini demo day in the BSC Atrium. And so I thought about moving it a little bit later. We could do that. I do have the Micro 2 demo day, I think is the 19th or something. I can't remember. Let's see. What date is that? 7th. I think the Micro 2 is the 19th. So we could move it back. We could move it back a week or even almost 2 weeks. So I don't know. I'll think about that. But what I think I'm going to do instead, I think we'll go ahead and we'll shoot for the 7th. That's a whole month. And then if somebody can't make the 7th, then they can present on the 19th, but it will cost them a letter grade. So we'll do that. So something like that. But anyway, so I think we should be able to do the 7th. Should be fairly doable. Let's see, is that what I said? No, not the 7th, April. It's the 11th of April is the demo day, and I think the other one is the 23rd. Yeah, I think that's right. So if you miss the 11th, you can save having to get an incomplete by presenting on the 23rd. I may set that up. I don't know. I'm thinking about that still, but I really would like everybody to do it on the 11th. And usually what I do, if you don't present your final project on the 11th, you get an incomplete in the course, and then in September you have to finish it up. Okay, and then you get a grade when you get it done. So anyway, you remember you have to do all the labs, save one, and you have to do the final project, or you get an incomplete in this course. Because that's what you need to learn out of this course. Okay, any questions about demo day? And then we're going to talk about the final project in great detail. The other thing, I won't go over the test because I don't think, I don't guess Ann Schul got them graded. So we'll hopefully have those back and give them to you after spring break. I'll probably, if I get them from Ann Schul over the break, I'll post them on Blackboard. So if they pop up on Blackboard, you can see them. But we'll pass them back and we'll go over the test the first day we're back. Okay. So I wasn't going to do a little demo, but I think what I'll do is talk about the final project first. And so let's do that. And then this will probably take a while because I'm going to go through. So I brought a bunch of parts. I finally got them a lot better organized. So I've got a whole bunch of parts here, and in fact you can even buy for like $15 or $12. You can buy a bag of 25 different things you can interface to your. They're really set up for the Arduino, but you can do the same thing with the PIP. All right, so let's talk about it. So, oh, I did want to mention one other thing. We will have a practicum. I think that's the week we get back. Let's see. Let's see. So let's see, the practicum is on the 28th of March. So we'll be back. Yeah, we'll be back for a week. Actually, it'll be the it'll be 2 weeks after we get back, or even 2.5 weeks. So we'll do that practicum then. Here's the way the practicum is going to go down. So you'll come to, you probably should form up into teams of 1, 2, or 3 people. It's probably best to have some partners, but if you don't want to, that's fine. And you should bring your laptop and your Viva board. And then I will pass out some things to hook onto your Viva board. There may be modules that plug into your analog port. They may be extra LEDs, and then you'll have the laboratory period basically to write code and demonstrate a solution to the problem you're given. Everybody will have a slightly different problem. So you should go ahead and have some shell code set up so you don't have to start from scratch with your configuration variables and all that. Yeah.
Is it going to be in C or assembly?
You can do it either one, but probably best to do it in C. But it depends. Maybe it might be easier in assembly for some. You're welcome to use either one. And then basically the first thing you have to do is you have to demonstrate that you have your Viva board. So you should bring your Viva board in to class with a blink routine on it, so I can see you blink one of the colors in your RGB LED. And that way I know your board's working and you can program. And you should bring in a battery to power your board, so you don't have to worry about that, or at least, or maybe a USB plug. That's fine too. I think the classroom has. I think there's power in some of the socket. Yeah, there's power available. I think all the seats have power somewhere down there underneath them. So go ahead and so you can plug in your laptop and whatnot. Make sure you have the IDE. At least if you partner with somebody, then you don't have to have it on your laptop, and you don't have to bring your laptop. But make sure one of your partners does. And also, somebody needs a programmer. So make sure somebody's got either a Snap or a PicKit3. And make sure that this isn't the first time you've ever used your board. That would be a bad idea. Make sure your board works, that you can program it, that, et cetera, and et cetera. So you should come into class ready to go. Because if you already have a program made and you don't have to start from scratch, that'll save you, 4 or 5 minutes, maybe longer if you're a little slow at getting that stuff done. And so you're just all ready to go to start writing your code. So you should have your configuration files all done. You should have your XC8 header file in place. You should have the stuff to set up the clock at 4 megahertz, and then you can change it if you need to. But you should make sure you can get to a copy of the data sheet so if you need to check something. And I haven't decided exactly what I'll do, but I may have you A to D I may have you use a photoresistor as one of the input devices, and maybe blink one of your RGB LEDs or something. So we'll definitely give you some things to do, but you may have to use the A to D. You may have to configure for LEDs. We'll see. You may have to configure the timers or screw around with timing loops. So, but it'll be something that should be very doable in the, in say 20, 25, 30, 40 minutes. And since we have an hour, what is it, an hour 15, you should have plenty of time to get it done. And if you don't get it all done, then you get partial credit. Okay, so that's the practicum. So make sure you're, we've got a little bit of time left before we're going to hit that, so that's fine. But that is coming up on the 28th of March. Okay. All right. All right. So you've already used interrupts, and we've talked about those some. So I probably am not going to talk too much more about that today. And then you've already used A to D. You've touched. You've used the UART sort of. We were supposed to get that done, but we didn't. We haven't used SPI I2C yet. We'll talk about that. Not today, but we'll cover that. But today, what I'm going to really focus on is the project. So let's see. I think I said most of this. So one of the reasons. So why do we do a project? Why do we do a practical? Well, really, you basically have to have the ability to write code if you're going to use microprocessors, and you also have to know how to electrically interface them. And you also have to be able to develop algorithms. And so these are skills that you can only learn by doing, really. I know that what I say in lecture, I'd like to think it's somewhat helpful, but I know in the end, it's what you do in lab that actually gives you the confidence to be able to interface a microprocessor. So I know that's really key. There are a bunch of steps that you have to do to implement an algorithm. And sometimes you have to calculate stuff, sometimes you have to move data around, sometimes you have to do some decision making based on the data and then control some actuators. Maybe you even have to write a control algorithm. But typically our algorithms are a set of ordered steps. Now, we are moving to a world where we're going to try and do as much in parallel as we possibly can. Because if you think about it, if you can take your algorithm and convert it from a mostly serial algorithm to a parallel algorithm, then for another $1 you can have another processor. For another $10 you can have 10 more processors, and you can have if you can turn your algorithm into a parallel algorithm, then you can do all these steps very, very fast because you can have each piece being done by a separate core if you want. And at the cost of cores and microprocessors, it really makes a lot of sense to do that. You have to be able to code up the steps, translate your logic steps into code, and then you have to be able to it's really nice if you can make these steps mostly self-contained, because then it's easier to kind of modularize it and test each piece as you go and not have it all sort of interdependent, so that if there's a single thing that's wrong, then you have no idea where to start to fix the code. You need to usually define the task very clearly. In the practicum, I often see students start off gangbusters, but they didn't read their task on their sheet, and so they kind of start off and they just don't understand what they're supposed to do. And so I'll make sure when we do the practicum that I have some examples actually running up here on the desk that show you an idea at least of what yours should look like. So make sure you clearly understand the task. And then before you just jump in, you ought to think about several different ways to approach it. One of the things that I've done in practicums before is I've had people have to write code to take 2 LEDs and blink one 3 times, and on the third blink, blink the other one simultaneously with the first one, without having some big gap in the blinking in the rhythm, so that it still goes exactly like it should, only the third time we just blink 2 instead of 1. Or maybe the third time we blink 1, and then in the off period we blink the other one. And people try and write very complicated loops to get this done. Turns out it's much better to just do it in one straight line code and then loop the whole straight line code, as opposed to trying to have a loop where you're blinking one light, and then when you count the 3 or 4, then you blink the other light. That gets a little tricky, although you could do that. But if you make it too complicated, it just takes more time to get it debugged and working like you want it to. And it's always better if you can make it simple as possible, especially when speed's an issue. And it turns out, in almost everything you do, speed is an issue. Because you're trying to get a product to market, and a lot of times that code is really the long pole in the tent. And whether you save a few program memory locations or not doesn't really matter. And how fast the integrated development, the embedded controller in your washing machine runs, as long as it runs fast enough to control the washing machine, everybody's happy. If you don't want to spend another 6 months trying to make the code just perfect, you really want it to be, you want the code to be robust and work, but you don't necessarily have to make it optimized. Or maybe you do in some cases, but in most cases you don't. Make sure you understand the trade-offs. Speed versus size and other things depending on what's important. Get it done versus elegant. Easy to follow or super clever but hard to follow code, because you won't be there forever and somebody else will probably have to mess with it at some point. And then leave space where you might come back and add in all sorts of additional features, but you don't put them in today because today you just want to get it done. Make sure you understand all the steps in some level of detail and a clear picture of what the outputs have to be. And then do a little block diagram. So create a little block diagram of how it's going to work, and maybe even a little sample flow chart of how the firmware is going to execute to make all the pieces of the block diagram work correctly. So you want a block diagram of all the modules and pieces, and then you want a flow chart for how the code's going to make things work and how it's going to flow. The flow chart, don't spend a lot of time on this. It just needs to be at a fairly high level so you get some sense of what some of the critical steps are and where you need to, how you can modularize your code and write and debug the pieces individually and then put them together. It should work. One of the keys here is you have to learn how to solve problems. Well, how do you learn how to solve problems? You learn how to solve problems by solving problems. I mean, that's really the bottom line. That's why I assign these projects and practicals. Okay, so here'd be an example of a typical project. I'm going to go through a bunch of other things. I'll go through all. I've brought in all sorts of goodies, and so I'll hold those up and let you see, look at those. But one of the things so we're going to use the Freedom Board with your PIC 16F1829. You can't do your project with an Arduino. Sorry. It would be easier because the code's already been written for almost every single interface device you can imagine. And that's nice and it's great. And actually I encourage you to get an Arduino, and when you get ready to do a project and you go out and you buy, let's say you go out and you buy maybe you buy a little OLED display. Well, go ahead and plug it in, hook it up to your Arduino, run it on the Arduino, make sure it's working on the Arduino, because that way you know your module's good. I often use Arduinos to test the parts I get to make sure they're working, because usually there's code out there. All you got to do is download the file, click on it, do the example, boom, it's running. And then you have confidence, okay, when I hook this up and write my own code and it doesn't work, I know it's not because the module is perfect. I know the module actually works. And sometimes I'll take it and I'll put it back on the Arduino. Okay, yeah, it really does work. I haven't blown it. And that's very helpful to take that question mark off the table. Then you can focus on your code. People always want to blame hardware, and occasionally hardware is the problem, but normally it's your code. So let's say you want to have a temperature probe and you want to read in the temperature value, which will be this particular probe, say, is an LM35. So it sends you a voltage level that represents the temperature, or maybe it's the little device that Microchip makes, and same thing. A voltage level is correlated with temperature. So you're going to have to use an analog to digital input in order to get that voltage value into your microprocessor, so you can figure out what the temperature is indicated by that sensor. And then you take that voltage value and you have to crunch it with some mathematical equation. You have to scale it, figure out the voltage based on your A to D, going from, say, 0 to 5 or 0 to 3.3. Or maybe you're going to change it and go from 0 to one of the fixed voltage references, because that's 0 to 2048 or something like that. Sometimes make it a lot easier to decode the voltage. Anyway, so you have the temp sensor, and then you're going to display this on a 2x16 LCD display, and you're going to talk to that 2x16 LCD display with an I2C bus. So that's a nice little project. And so we'll hook all this up. So you're going to have to do the temp sensor, the LCD display, the A to D peripheral module, and the I2C bus protocol and peripheral module. You're going to have to configure all this stuff and get it hooked up. And so that would be a great project. This would be fine for a team of 3 people, because there's four modules/sensors involved here, and so that would be it. That's perfectly acceptable. We will do something similar to this in lab, so you have to be a little different than the exact lab program, but as long as it's got a little different twist to it, that's fine. All right. So here's some of the sensors. So obviously, one of the things we have are the pots, and you guys are familiar with these. So you can interface a number of different ones, but some of the easiest ones to interface are these ones that we kind of already have used in lab with the wires and everything. I guess I should put these over here. So some of these have been burned by people. What's that? Oh yeah. So some of these have been burned because there's a little piece of carbon film and there's a wiper that runs across the carbon film. And if you put this, normally what we do is we put the two the opposite ends of the carbon film we put from ground to VCC. And so maybe it goes 0 to 5 volts. And then the wiper is usually what we feed into a pin. But if you put the wiper to ground, this terminal to ground, and this one to VCC, and then you turn it really close to, you turn the wiper very close to the VCC level by turning the little wheel, then eventually you get down to almost 0 ohms, and it'll heat it up pretty good, and it'll burn it. And then the pot doesn't work very well, and it's all screwed up. So try not to burn the pots, although a number of them are burned. And the first thing, and the other thing, even when you're just doing a project with your analog to digital converter, it's really nice to go ahead and plug this, the 2 wires that are the same color in the ground and VCC, put the wiper into the A to D input, and then as you turn the wheel, you should go from your minimum reading, which is 0, to your maximum reading, which is 1024. And you should see that would be 3FF, I think. So you should see, no, actually, it's 10 bits. It's 3, 8, 9, 10. So it's, it's 3FF, exactly. So you should go to 3FF. And that's a, if you don't see, and it might not be exactly, it might start at 2 or 3 and go to, 3FE or 3FD or something, but it should be pretty close to that. And if it's not, your A to D is not working correctly. And that can be a real healthy way to test your analog to digital input using a pod as just a test device. Okay, so we have a bunch of 2-color LEDs and 3-color LEDs, although you have a 3-colored LED on the board, so you probably don't need to add another one, but you can if you want. Or you can add a whole bunch of them and create some kind of fancy thing. Real-time clocks. Okay, so we have a bunch of real-time clocks. They actually come in several different types. I don't know if you can see them very well here. But so there's one like this, and usually these real-time clocks have a built-in battery, almost always. So this one looks like this. It's got a little built-in battery. It's typically rechargeable, although not always. And then this one, same thing, only it's got a bigger battery. It's got an LIR 2032 that's rechargeable. It's a lithium ion, and this has a CR 1220 that's also 3 volts as opposed to 3.6. Anyway, the nice thing about so this one runs on its own. Well, almost all of them have this little crystal, and these crystals are always the same. They're always cut to the same frequency. It's I forget. It works out that it's about the number of seconds in a day or something, and so it works out pretty well for synchronizing these clocks. And they usually have some temperature compensation built in too with the crystal, and that's what this little long piece is right there. Let's see it very well. So this little long piece. This is a crystal. You can see if I angle it a little bit, maybe. Yeah, you can kind of see it there. I don't know, it's hard to see. It's kind of shiny. And this one has the same crystal on it, right there. But it also has, maybe it's better down the line. Yeah, a little bit. So it has the same crystal right there, but it also has, interestingly, it has a built-in electrically erasable, electrically programmable read-only memory. And most of these, some of these interface with I2C. This one actually doesn't interface with I2C. It interfaces with a series of pulses that you can read with a GPIO port, and it's a proprietary thing. It's kind of confusing. Whereas this one is a little more straightforward. It sends ASCII characters over the I2C line, and then you can also use you can also talk to the little EEPROM that's on here too. That's also addressed. So you have 2 I2C packages on this same board, each with a different slave address. You can talk to whichever one you want to by using the right slave address. So that's kind of a nice little feature. Okay, so that's the real-time clocks. And then what you can do, even when you power it down, if the battery's charged up, it'll continue to hold the time for quite a while. Maybe a week or so. So as long as you power it up, every week or every now and then, it'll continue to work for a good long time. and that's it's kind of fun to have the real-time clock thing going. And you can display it on a 2-line by 16 LCD or some other display, and you can make your own alarm clock with your little Viva board. So, so that's kind of cool. All right. So that's real-time clocks. Okay. So we also have temperature sensors. So within our so one of the labs we're going to do, we'll have some. I made some little plug-in boards that plug into your analog header. So here's the little plug-in board right here. So it looks like this, and it takes power, ground, and then it plugs in directly to your analog header. You have to get it plugged in correctly, and it should go in like this, just like that, to the analog header. And you can kind of see it a little bit there. So it plugs in there, kind of like that. And on this little gizmo, it's got two things. It's got a photoresistor on it, and it's got a temperature sensor. And the temperature sensor is the MCP 9700. And this is a part made by Microchip. It's in one of these SOT3 or whatever. No, it's not. I forget the designation. But anyway, it looks like a transistor, but it's just a temperature sensor, and it has 3 pins: power, ground, and the temperature out. The temperature out has to go as an analog signal, and we put a couple of capacitors on here to sort of buffer the power and take away any noise, hopefully. And both these sensors have to be, and actually one of the resistors creates a resistor bridge with the photoresistor, because that's the only way it works. You want it to vary a voltage, and so if it's going to vary a voltage, then you're kind of stuck having to create a bridge. So here's your photoresistor, and then here's a fixed resistor, and then you connect that, say, to ground, and this to VCC, and then you read then this to an A to D port. And so as this resistance changes, the voltage here varies, and usually we make this like 10K or something, or maybe bigger. And this usually varies from like 500 mega ohms to maybe 30K. So it won't go the whole distance from VCC to ground, but it'll change the voltage enough that you can sense the difference in lighting conditions, and it's very useful for a lot of things. And they're super cheap. You can get them for just a penny or two a piece. So it's a really nice little thing to have. Okay, so that's this. This little gizmo here is an LM35. Looks a lot like the MPC 9700, and it is. It just has different calibration. It's a little nicer to use than the MCP 9700, but they're a little more expensive too. And anyway, I had a bunch of these when I made these boards, so that's why I put the MCP 9700 on it. But anyway, these are both nice temperature sensors, and they have very little self-heating. All temperature sensors, because they take power and ground, they have a little current running through them, so they do a little self-heating. But the self-heating on these, if you read the data sheets, guaranteed to be just a tiny fraction of a degree. So, and of course, if it's in a real insulated spot, it might be a little more and whatnot. In the open air, it'd be a lot less probably. Anyway, so you can use an LM35 standalone by itself, or you can use this little board with the MCP 9700 on it. And those are definitely options for you. All right. And we'll do a lab with that little board, so you'll have some experience with that. All right, so LCD displays. So we'll talk about these. We'll do a whole class on LCD displays, and there are a couple of data sheets, and there's a bunch of code on the Blackboard to interface these. And there's really two different. Here's what they come in: a number of shapes and sizes. They come. So this is. But in any event, you have to be careful with that. And I have a bunch of both because, well, that's just how it was. Anyway, so it's a standard 16-pin interface. 2 of the pins are just for the backlight. They have a built-in backlight, and I'll show you. We'll talk about this at some length in this class, and we'll do a lab where you have to interface one of these to your board and send out data and display it. The screen basically takes ASCII characters, but you have to you have a 1 pin you set high or low depending on whether you're giving it data to display, like a character, or whether you're giving it a command, like where on the screen you want it displayed, and turning it on, and what format, and clearing the screen, and things like that, and positioning the cursor. And so you have all the commands that control that kind of stuff. So that's a 2-line by 16. There are 16. You can display 16 letters across and 2 lines worth. Then you can get a 4-line by 20. You can display 20 lines, 20 characters across, or maybe just 16, depending. I don't know if this is a 20 or 16. I think it's a 20 here. And then you can actually have 4 lines of 20 characters, and that's the maximum amount of information these will display is 4 times 20 or 80 characters. And then you can have these where we interface the pins directly to the pitch, and you can use all 16 pins can connect, or you can get, well, you don't need 16 because 2 of them are for the backlight, and then 2 of them are ground and power, and then 1 of them is a contrast. So when it's all said and done, that's 5 pins out of the 16. So you only need 11 pins on your board. But that's a lot of pins. So if you want to get by with fewer pins, you can do what's called a 4-bit interface instead of an 8-bit interface. And now you can get by, and then you can not read the display by taking the read write line and grounding it low. And so now you can actually get by with 6 pins of a direct interface. But there's an even better way to do it. You can put one of these little daughter boards on it that has a built-in chip. It's got a PCF 8755 or whatever, something like that. And that chip basically takes your I2C information and turns it into an 8-bit interface. So you use 7 bits for the display, and then 1 of the bits is to turn on and off the backlight. And so that's another way to do it using I2C. And so we have all those options pretty much available. And you can even create, we've even had groups create their own characters and create a little Space Invaders game or that sort of thing. So there's a lot of pretty cool things you can do with these displays. They're actually pretty cool. Pretty powerful and pretty good. Okay, so and we will do labs with those. Okay, so that's the LCD displays. I2C, so we talked about that. So the LCD, the one LCD comes with a little board that allows you to address it with I2C. And again, I have all the routines for this on Blackboard. You can also use I2C to talk to a lot of other modules out there, some of which we have, some of which I don't have. But there are a lot of I2C devices available. What that stands for is Integrated Circuit Communication. So IIC, and that's, or I2C. And that's actually exactly what it's used for. And the other, of course, serial interface that's used a lot, chip to chip, is SPI. I2C only takes 2 lines. SPI typically takes 4 if it's fully implemented. The SPI is much faster. So sometimes if you need to do video or very high-speed audio, you probably need to use SPI. If it's relatively slow, you can use I2C. And then obviously we've used the UART stuff to the terminal program and that sort of thing, and we'll do that some more. Okay, you can actually do real RS-232, although this used to be more of an issue when almost every computer, before USB, every computer had RS-232 ports on it, so you actually had to level shift your TTL levels using this MAX 232 chip. Now we don't have to do that so much because RS-232 is kind of gone by the wayside transmission protocol. But we certainly still use the UARTs, and we just usually use a UART, TTL level UART to USB converter. And what that means is, when we say TTL level, we're talking about 3.3 volts or 5 volts instead of the RS-232 levels, which were plus or minus 15. And you had to generate a minus 15 and a plus 15 volts, and that was a real pain. So it's nice to be able to just let your microprocessor send out its UART signal with ground and 3.3 volts instead of having to convert it into plus or minus 15 volts. But if you need to do that, you can with one of these MAX 232 chips that'll actually generate the minus voltage for you using a charge pump with extra capacitors, and then it'll convert all your signals both directions. So it's a nice little interface chip, but we don't use it too much. Okay, ping sensor. So a ping sensor is a nice ultrasonic sensor. I think it runs at 48 kilohertz is the audio frequency, and it has a 4-pin interface. There are some 3-pin interface ones out there, but these are all 4. It's got a built-in little clock here, and then it's got two ultrasonic horns. One is a transmit, one is a receive, and then it's got the interface and drive circuitry on the back. The way this thing works is you've got ground power, and it usually runs at 5 volts. So you've got ground power, and then you have trigger and echo. The trigger line, you have to send out like a 20 millisecond pulse, and then what happens is so that you have so here's your trigger, and here's your echo. So the trigger goes out, and you send a little 20 millisecond pulse, and each time you do that, it sends out its ultrasound, bounces off something, and comes back. It recognizes it from all the other noise around because it's a little burst. It's like I forget, maybe a 10 cycle burst of 48 kilohertz or something like that. I forget the exact frequency, but it's in that ballpark. And so it sends this little 10 cycle or 8 cycle burst or whatever it is. And so when it comes back, it filters for this frequency. And again, I may not be remembering this right, but it's all on the data sheet. And so then it detects its signal. And so then what it does, after the pulse, at some point here, it raises the echo line and keeps it up, and then it goes down. And the time that this represents is the time of flight out and back of the ultrasound pulse. So now all you have to do is use the time and the speed of sound and divide this by 2 because it's a round trip time. So you only want one of the measurements. And then you can actually do distance. And it's usually good for maybe 2 centimeters, maybe out to, in a quiet room, with a great reflector, you might get maybe up to say 4 meters or something like that. Something like that. It could go a little more, maybe a little less. It does have an absolute limit though, because it times out. If it doesn't see its echo within so many milliseconds, it times out. And that's the maximum distance you could ever record. So that's the ping sensor. And so that's a nice little way. A lot of little robots use these things to avoid obstacles. And you can actually have a little powered cart that your board sits on, and you can drive it around and miss obstacles with your little ping sensor. I have one where the ping sensor is controlled by a servo, and it's continually scanning back and forth like this. So it's actually one ping sensor is covering almost 180 degrees front looking. It's kind of cool. Maybe I'll bring that in sometime and demo it. That one uses a basic stamp, so it's a microchip part. It's a much simpler microprocessor than we're using actually, but it's programmable and basic because it's a basic stamp. All right, so now we have so that's the ping sensor. Servo motors. Okay, so we have lots of servo motors, and so this one is continuous rotation, and then this one is just goes through 180 degrees. The standard servo has typically a plus or minus 90 degree turn, but they do make some specialty ones you can get, like this one, that go forward or backward, and they go slower or faster depending upon the signal you send. So it's the same signal that you would use to position this from minus 90 degrees, 0 degrees, and then plus 90 degrees. And only in this one, it just makes it rotate faster backwards or faster forwards the further away from 0 you get with your signal. And the standard, these are always controlled by PWM. There is a new servo in town, and it's called a digital servo, and they have the ability to use the same signals that these use, but they also have the ability to actually do a GPIO interface where you actually send out data, or maybe it's I2C, but where it actually takes a digital byte, and then that sets the angle. And all the processing is done inside the servo. And that's probably, eventually I'm sure we'll just go to all digital servos probably. But servos have been around for a really long time. There's a lot of them out there, so it's going to be a while before we make that transition. Okay, so that's servos. And the, yeah. Did I have those? Did you see those? Okay. So, servo motors. Timer module. So you've already used the timer module to adjust the blink period for your LED, and you can definitely use timers for other things. For instance, when you're measuring this echo thing, really the best way to do it is to use the gate on timer 1 and let this pin drive the gate. And so when this goes high, timer 1 starts counting, and then when it goes low, it stops timer 1, and then you just have to read timer 1 when your pin goes low. And you don't have to worry about the sloppiness of your timing loop pulling this pin. It's going to be very precise if you're driving the gate of timer 1 with this. And you can also run timer 1 at a very high clip. It's a 16-bit counter, so you can be ticking away pretty fast and get a very accurate count that way. So, and since you're doing it in hardware, you know that it's very tightly coupled to the edges of that signal when it stops and starts that timer. So that's a good way to do it. You don't have to do that. You can sit there in a loop, in a for loop, and just look at that pin and start incrementing the counter when the pin's high and stop incrementing when the pin's low using a nested for loop or something like that. But or one of our delay routines. But more accurate is to do more of it in hardware. And so you've used timer modules for that. Okay. So the D to A output. So I'll talk a little bit about this. So our digital to analog converter on this chip is not very robust. It only has 5 bits of resolution, so it's not the greatest in the world. But it will work, and you can do some stuff with it. But you can also do that with your own loop. So let me show you. I'll show you a little. Let's see. So this. Let's see. Can you see that? All right. So here's this this little test piezo thing. So what I have here. So this is kind of interesting. I'll show you a couple things here. So I have mounted in here a little piezo buzzer, but I think I'm going to take it off for a second. And I'm going to show you. So these little buzzers are kind of cool little devices, and they come in 2 flavors, and you kind of need to know the difference between them. Now, if you look at these, they look pretty similar, don't they? But they're totally different, okay? And half the time you can't tell by looking at them. You just have to read the data sheet. So this one, so I'm going to hook this up, and I'll show you. So this one, and they both are polarized. So you have to get the positive pin to the positive pin, otherwise they just will not work. And so, and on your little green terminal, the positive pin is on the left side of the terminal. So it's closest to the little Vivo logo there. The positive side is this pin here, and the negative is the one over there. All right, so I screwed it in, hopefully correctly. And now, I don't even have to worry about what program I'm running. I'm just going to take this jumper wire, and I'm going to jumper from VCC straight to this. And you can hear it makes a nice tone. Okay? So if you want that one, you have to make sure you get that one. Now, I'm going to switch it out here, and I'll hook up the other one, and I'll show you the difference. And it's kind of embarrassing when you do a project, and you expect it to work great, and your little buzzer doesn't work. And that's because you didn't read the data sheet and realized you bought the wrong buzzer. And so here's the deal with this one. Now I want you to, so I'm going to do the same thing here. I'm going to power it with the battery power. Now listen up. Can you hear it clicking? It's not making a tone. When you power it, all it does is move the little piezo diaphragm a little bit. And then when you unpower it, it goes back. A little bit, it goes back. But if you do this at a very high rate of speed with your microprocessor controlling it, now it works really cool. So for instance, so that's the A, the S, and the T. So now I can actually drive it at different frequencies because I'm changing the timing in my loop based on what touch button I touch. Okay? So if you want to have the ability to play different sounds, then you have to buy the other one. But if you didn't want to do that and you thought you just had to give it 5 volts and away it would go, make sure you get the right one for that purpose. Okay? So there's all sorts of little hidden pitfalls. One of my former students built this little refrigerator monitor. He works at a medical device company, and they have these expensive reagents. And somebody left the refrigerator door open on a Friday afternoon, and all weekend a bunch of chemicals. They lost $30,000 worth of stuff in the refrigerator over the weekend. So they asked him if he could figure out a way to help, and so he made this little buzzer thing that would ring if the refrigerator door was open. And so anyway, and then he bought a website and he's trying to market it now. Yeah, right. Who knows? He'll probably be wealthy someday. Eventually, one of his ideas will pay off. So anyway, but he bought the wrong buzzer, and he wanted the one that just worked on 5 volts. He didn't want to have to. He actually didn't even put a microprocessor in the circuit, but so he didn't have the ability to generate his own tone, and so he wanted the other one, and so he was kicking himself that he didn't read the data sheet carefully and got the wrong one. All right, and that's a pretty sharp, pretty experienced engineer. Okay, let's see what happened. Okay, so that's our little DDA. You can also use the DDA if you want, and instead of having a loop tied up making the tone, you can use, say, the PWM channel, and you can program it. And once you program it, it'll just sit there and continue to play that tone while your processor goes off and does other stuff. Or you can have a fancy, complicated tone by generating some kind of fancy signal with the D to A that might have a couple of harmonics playing at the same time or something. Okay, USB interface. So as you know, in lab this last weekend, when I was in Colorado, we didn't have the little module. So there's a whole bunch of these modules available. And let's see. So this one is what's called the 2102, and it's already set up to plug directly into the header on your Viva board. It's all set up to do that. It's just ready to go. And then all you have to do is plug it into your laptop, and then you just have to bring up PuTTY, and you have to know what channel it is. So you go to the device manager. Now you can, if you want to write your own routine, you can auto-detect these things. So there it is, standard serial link. Okay. Now it is. Silicon Labs CP210X, in this case a 2102, USB to UART bridge COM14. Okay, great. So now I'm going to boot up PuTTY, and I'm going to put it in serial mode, COM14. Oh, it doesn't like it. Oh, I see. Numlocks on. 14. And away we go. And so it's sending out this information. It's actually kind of hard to see because I didn't really format it very nicely. But if we stop it by pushing this. You can say this is my T count. This is what you should have seen printing out. And it shows you the touchpad, and you can see those numbers change when you touch it. Anyway, so and you can actually format that and send all sorts of stuff, or you can write your own. You can write your own C# interface or Visual C interface, and you can have some pretty fancy communication with your microprocessor using this UART. You can definitely send information both ways. And you can write code on your micro side to interpret the data coming in. You can send data out. You can display it. You can even display it as like a graph, all sorts of things. So it's very powerful and it's very nice. And that's a great way to talk to your laptop or desktop using one of these. And if I'm not using it, it doesn't affect the program. The program still works, whether I use it or not. So it's still working just fine. Anyway, so that's that. And I actually bought enough of these. I struggled with whether or not every student should buy one. So I have enough for every student to buy one, but we've normally just been using them in lab. But anyway, I don't know. We'll see. I still haven't decided what's a great idea. But if you want one, I'll probably put some in the parts bin so you can get them if you want. They're only maybe a couple dollars each or something, and then maybe $1 for the cord, or maybe $1.50 for the cord or something. I'm not sure how much they cost. The cords are probably as expensive as the modules. Okay. So continuing. So IR remote reader. Okay. So this is a nice little device. And it's a very cool little interface to do. So let me show you that. So I have a number of these, and they look like this. So I'll take it out of this little bag. So it comes with a little remote control, and you do have to have the battery. You have to put a battery in the little remote control thing. So here's a little remote control. I don't know. This is no, I don't think this has ever been used. But you have to call it this little slide and push this little thing in, and then you put a little coin cell in here, and then when you punch with these buttons, it sends out using this IR output. It sends out a little signal, which you can actually, if you're not sure if it's working, then you can take out your cell phone. And on your cell phone, you can watch it, but you can put on the camera. But you can't see it, typically, at least on the iPhone, you can't see it on the main camera on the back because they put an IR filter on that one. But on the front-facing camera, they don't put an IR filter, and you can see it on that one. Maybe on the Samsung, you can see it on both ones, both cameras, because they don't put on an IR filter. And then on the other side, on the micro side, you have this little IR transistor. And it looks like this. It's in this little fancy container for some reason. And it's got 3 leads, and then you just connect those to the micro. And again, it's power, ground, and a voltage in. And the voltage in then detects when it sees this infrared signal. And it's pretty sensitive. And when you get the signal, if it's powered up, it'll blink this little LED on the board so you'll know you're talking to it. And then what you have to do is you have to write your own custom algorithm to decode the signal that this is sending out. Now, there are a whole bunch of different protocols that our little remote control devices use, but there's one that's very standard. It's a Philips standard protocol, and that's what this uses. And most devices use the Philips, although Sony probably uses their own, and I don't know, other Hitachi probably uses their own. So there are different ones out there, but a lot of them will use this Philips standard. And so you can then write the code to do this. I've only really had, I think, a couple of groups of students that have done this for their project. It takes a little bit of work, but it's pretty cool to get that decoded. And you definitely learn quite a bit doing that. So anyway, so that's available. We have a bunch of those. And so that's an option. Okay. And so that's a IR remote reader. Then we have an RFID reader. Okay, so that's kind of cool. Let's see. So here's this standard. All right, so this one's open. All right, so what this looks like. So it has a couple different choices on the little header, and so it's got a couple of. Actually, it comes usually with a couple of cards. So this is the device, and you basically put in the little header. Usually the right angle header is nicer, and then you can plug it into a little socket, or you can plug it into a little project board. So you can take a little project board like this, and you can plug this in here, and then you can connect to it, and basically then it has this built-in antenna that when you bring the card next to it, it'll read the card, decode it, and then it'll send out using SPI. Yeah, so it's an SPI interface. It'll send it out on an SPI interface to your micro, and your micro can have up to 2 SPI modules, so that'll work fine. And you can plug a bunch of SPI devices into each of the modules. You just have a different slave select for each one. So that's definitely an option. I don't think anybody's ever done this one, but you're certainly welcome to. I have a bunch of them, and it's kind of cool. I have thought about implementing this for and passing every student out one of the little cards. I have a whole basket full of the dongles, and that way I could do attendance without having to mess around with it. But then I'm sure somebody would probably give their friend their card. But anyway, we might do that one of these days. So if some student wants to do it, I'll use your code. All right. So that's the RFID reader. And then GPS receivers. So I have a bunch of those. They've gotten very cost effective. Let's see, where are they? Yeah. So they come in a number of shapes and sizes. In the old days, some of the initial ones look like this, with kind of this flat antenna here, and then the circuitry on the back, and this little module here with all and these will receive a bunch of channels. They're pretty amazing, really. Okay, so that's that. But nowadays these were usually maybe 30 bucks or so. They're kind of expensive. Now they're kind of cheap. I don't know if I have one open or not. Anyway, they're not too bad at all. They have their own little antenna built in, anyhow, if we open it up, so this is what it looks like. Oops. So it has just these two pieces, and I guess you have to get your own header. So anyway, solder on the header, and then you plug it in. It has the same kind of little module, but the antenna then is this little thing here, and so it plugs into a little small antenna jack, believe it or not, right here. And so it just pushes into that little antenna jack. I don't even know what size. And then this is the actual antenna, this little gizmo here. And if it can see the sky, it can receive a whole bunch of channels, and in both of these modules, they take power, ground, and then they communicate. Typically, they communicate with a UART. So it's really nice. And then usually it's got one little pin on here. This one does, for sure. You scroll in. You can see there's a PPS pin at the top there, and that PPS gives you a pulse per second. So you can actually use it as a, and no, let's see, wait a minute. So. So these are kind of interesting. They're pretty sensitive, and they're what's used in a lot of security systems. And you can see them built into security lights, where they'll automatically turn the light on if they see any motion. And so they don't transmit infrared. All they do is look for an infrared signal, and then if they see one, if it exceeds a threshold, then it activates. And so here's what they look like, and they have a couple of adjustments on them. They're pretty standard. They're like all basically about the same. So you can see it's got a bunch of components on the back. It's got 2 ICs and a bunch of capacitors. It's got the interface, and the interface is basically power, ground, and the oh, sorry. So here's what it looks like. That's the sensor side. It's got a little dome on it. And then you see the 2 pots here. And the 2 pots, one sets the sensitivity level, the threshold at which it'll turn on, and the other sets how long it stays on. It's got that capability so you can drive a light with it. And you don't even have to have a micro. But if you have a micro, you can do all sorts of other things. So your pin basically is your power, ground, and the middle pin is your signal out. And that signal out is either a 1 or a 0. So the decision is basically made in the board whether it's what the threshold is. You'd have to hack it if you were going to change the threshold on the fly. But you can change it, of course, with a screwdriver. But the micro can't change it directly. You'd have to interface. All you'd have to do is put a D to A signal to it, and that would probably work just fine. Okay, so anyway, so there's that. And that's a passive infrared sensor. And so that's an option. Okay, and then we have a joystick. So we have a bunch of joysticks. Let's see. So here. So, of course, they come in all sorts of shapes and sizes. But here's this one, and it's got a little knob that goes on the top. And basically, it goes in 2 directions, and then if you push it, it indicates if you push it, it's actually a switch. And so you can fine-tune it with the little pots on each of the axes, so it's 2 axes. And then if you push it, you can see it drives this thing down and pushes this little button. So the interface is power, ground, X, Y, and the switch. Okay, so you can interface this, and you could do all sorts of things. The X and Y are analog values, and they're going to be a voltage from power to ground. So you have to A to D those. So you basically can plug this directly into your. You can take this and plug this. It's exactly compatible with your port. You can plug it in just like that, and it'll work fine. So there's an option. Okay. So that's the joystick. So anyway. All right. Okay, then Bluetooth. So Bluetooth comes in a couple of different flavors. There are dongles that are called standard Bluetooth, and then there's Bluetooth LE, low energy. And so you can tell them apart by the antennas. Actually, it's kind of cool. So you can see the one that's got the matching leg on the antenna. is the low energy, and then this one, the standard. The standard comes in two flavors, master and slave. So some of them can be master or slave, but most of them are only slaves. So your laptop would be the master, and then this would be the slave. And what's nice is you can plug this into your Viva board as well. In this case, you actually have to modify the pin arrangement a little bit. So you have to use wires and move them around. But this header will drive it just fine. Power and ground. You do have to power these because the only source of power is going to be your Viva board. And sometimes this one says 3.6 volts to 5 volts or 6 volts. So normally you run these at 5 volts. So you can set your jumper for 5 volts and run them, and it should work fine. And then you can actually download stuff on your iPhone and your Android phones so that you can actually talk to your board with your phone. And we have a bunch of these in the lab too. So if you don't want to use the UART to your desktop or laptop, you can actually use it to your phone. The only thing that's tricky about doing Bluetooth, when you look at the number of signals in a room like this or in our laboratory, it's crazy. There's so many signals you can't figure out which one is your Bluetooth module. And the only way to tell is to guess, and then once you guess, if you pair with it, the red flashing light will go solid, and then you know you've got the right one. But in a laboratory, you know, one group was getting paired by another group, and they couldn't tell whose group was which group, and it was just crazy. So we kind of learned the hard way that didn't work real well, but it's kind of cool. But you have to have a little less Bluetooth action going on to make it really fun. All right, so that's Bluetooth. And then so I talked about the photoresistor already. So the photoresistor, it's actually a completely there's no silicone in it at all, no integrated circuit. It's a totally passive device, and it just has a photoresistive coating on it that changes its resistance when it's exposed to light. It's not a photocell. So there's a big difference between a photoresistor and a photocell. A photocell generates a potential from the light, and it can actually charge a battery and things like that. But a photoresistor has to be powered, and you have to create a voltage divider with the photoresistor, and all it does is change resistance. So if you want to measure something, you have to set up a voltage divider with another resistor across a power supply, and then measure it at the center point. Otherwise, if you didn't have this resistor and you connected that to ground, you'd always measure ground there. And if you didn't have it connected to any reference, you'd always measure VCC, because no current would flow, or very, very, very little. So as a result, it wouldn't work. You have to set it up as a voltage divider. And then the IR LED. So you can also set up your own communication protocol with IR LEDs and IR transistors, and the LED can flash away and the transistor can receive it. You can do that on your own without having to use the the pre-set up little controller thing. But you can do that too. And then we have communication RF modules. So we've got these they're called NR something 1024s or something, I forget. Anyway, so they look like this. They have a little antenna on them, and they're kind of they take a little bit of work to get them working. So that's a bit of a project. Again, this is the kind of thing where you want to probably hook it up to the Arduino first and talk between two Arduinos. But you can talk between two Viva boards with this very nicely. It does work. It's just it's a proprietary protocol. It takes a little bit of work to get it set up. And then we have touch panels. They didn't bring in the touch panels, but we've got those. And then there's a bunch of other stuff. So let me go through that. We're kind of running out of time. So one of the things that we have is we have these OLED displays. So they come in a couple different flavors. So one flavor is this little thing. And you can see it's not very big. And here's one that's actually even a little smaller. I don't know if you can see that or not. So this is one. You can see the little display surface is fairly small. It's just this amount right there. And then this one is about double the size. And they're exactly, one's 128 and one's 64 lines or something like that. But these are totally graphical, and they're very cool, and they're driven by an I2C interface. So it only takes 2 pins to drive these, and they're very nice. It's a little bit of a challenge to get them working, but I have some code, some existing code that would help make it not too bad. So. All right. Okay, so a couple of other things. So I have lots and lots of LEDs. I have some H bridges. So if you want to drive some motors, we've got that. I have a CO2 sensor, and I have alcohol sensors, so you can make your own breathalyzer. And let's see what else. We have some little touchpads you can interface. Turns out this looks really simple. 8 wires, 1 for each column, 1 for each row. But you have to scan it. You have to multiplex it. You have to power one. You have to power one set of wires and read the other, and then power the other and read the other. And you have to pull up resistors. And it turns out, because you don't want to count 1 punch as 100 punches, you have to have a little delay, and you have to kind of have a smart user interface. So getting a nice interface of this is actually a pretty good sized project. But people have done it, and it's actually, you learn a lot. Then we have a little, this is a Doppler radar. It sends out a radar pulse. This side is a radar antenna, and it receives the pulse, and it measures distance. And it has a, I forget how the interface goes. Yeah, it's got a, I don't know how the interface goes. I have to spend more time on the data sheet. I haven't used these, but they're amazingly inexpensive, and they really are Doppler. I mean, they really are radar. Very cool. And then let's see what else. So we have these are called hockey pucks. They're basically solid state relays, and this particular one is you can drive it with 3 volts DC, and it's optically isolated. And on the other side, you can put 380 volts into it AC, and you can handle 25 amps. So you can run a big motor with this. It's pretty powerful. And so I've got some of those. And then we have a little, this is a little IR sensor. It has a IR transmitter and receiver. It's got 2 little gizmos at the front. You can see 2 little LEDs on the front. One it transmits the IR, and the other receives it. The dark one receives it, so it's filtering out other light. So it's only sensitive to IR. So that's an option. And the interface of that is pretty straightforward. It's power, ground, and then it has a comparator on it. So you have a little potentiometer. You can adjust the sensitivity, and what it lets you do is basically detect objects sort of at fixed distances. And then we have a whole bunch of these. We have a whole bunch of these microphones where you can pick up noises, so you can make your own clapper. Anybody saw what is it? The Revenge of Frankenstein, the Mel Brooks film. Anyway, where they have the clapper. Okay, so that's another option, and then we have this. So this just interfaces an SD card, allows you to talk to an SD card from your micro. So that's an option. If you want to, yeah.
For our lab tomorrow, you want us to do lab 6 or 7 or both, or what's going on?
So hopefully, even though you didn't have the device to talk to your desktop or laptop terminal program, so hopefully you have all the rest of the code done, and you can just boot it up, hook up the device, and go. So we will have the 2102 devices ready to go, the CR2102s, And I'd like you to finish that lab, and I would like you to do the other one too, because I don't want to get behind. And the more of these labs you do, the more information you'll have in your brain to kind of help you guide in the project. So we'll try and do both of them. Okay, and then there's actually a few more things, but I can't think fast enough. Oh yeah, so we have a bunch of IMUs. So we have one with accelerometer and gyro built into the same chip. I2C communicated with I2C. Yeah, I think that's mostly it. Yeah. So I think that's pretty much everything. There is a bunch of other stuff too, but I think this is, anyway, it gives you a good idea. So you can see there are a lot of different things you can do. I have all the parts. I'll just have you sign them out. Some of them I don't care about, like LEDs and stuff, but some of the ones that cost $3 or $4 or $10 I like to get back. So be thinking what you want to do. At least come up with your group and sort of your initial proposal, and go ahead and submit that by Friday night at midnight. I'll change the link today so it's dated for Friday night. All right, we'll see you after spring break.